Donc, bonjour à tous, c'est un plaisir aujourd'hui d'avoir Gianluigi Rozza, d'abord en tant que scientifique émérite, détenteur d'une ERC et qui travaille à la CISA depuis quelque temps, et aussi qu'en tant qu'ami, parce que je connais Gianluigi depuis déjà de nombreuses années. On s'est rencontrés chez Tony Patera, et il a fait sa thèse avec Alfio Quarteroni. Donc, ça fait pas mal de temps qu'on bourlingue ensemble et qu'on a aussi quelques publications en commun, quelques travaux en commun. Et donc, c'est un plaisir pour moi de présenter cet exposé qui s'appelle Reduced Order Modeling for Parametric Time Dependent Nonlinear Optimal Control Problem. Et Gianluigi, the floor is yours.
Merci beaucoup, Yvonne. Merci, monsieur le professeur Madet. Bon après-midi, madame et messieurs. Je vais changer de langue. C'est un grand plaisir pour être ici et donner ce séminaire chez le laboratoire Jacques-Louis. This work that I'm going to introduce today is in cooperation with Maria Strazzullo, now at Politecnico di Torino after her PhD at CISA, and with Francesco, who is now at Catholic University in Brescia as assistant professor. And I wanted to collect the main topic, optimal control, also to celebrate the memory of Jacques-Louis. And I would like just to give you an overview and a brief introduction on what we did with optimal control thanks to reduced order modeling. And today I will introduce also a few applications in environmental sciences. We had also the need to be able to incorporate data simulation in our problem, and data sometimes are also noise is captured, and also sometimes we have some difficulties in the collection and also of course in working with data. And another important thing is that we wanted to focus on parametric optimal flow control, and when the parameters are related with physical quantities or geometry. And this is also useful for some problem related with uncertainty quantification or even parameter estimation. So we wanted to merge these two different development. On one side, numerical analysis of PDEs for optimal control and flow control, of course, based on PDEs as a state equation and constraint, the minimization of cost functional, and of course, the repetitive computational environment based on the fact that the parameterization is changing for several instances, and the parameter is indicated in the general notation of the reduced order modeling field mu. And with the reduced order modeling, of course, we need fast and reliable tools in order to be able to have, let's say, suited methodology for a repetitive computational environment. And the overview for today is based on the fact that I will focus mostly on the methodology. We will have the problem formulation, where we focus on time-dependent and non-linear PDEs. Then I will have a first example based mostly on more classical methodology based on proper orthogonal decomposition with a shallow water problem. And then I will focus on a space-time greedy in a more classic reduced basis context, and I will heat transfer based on, for example, on the Gratz flow. Then for the time remaining, I will select some of the applications. So there will be opportunity to talk a little bit about uncertainty quantification, environmental sciences. And if I have time, I would like to show also the application on optimal flow control in order to be able to control bifurcating PDEs, so bifurcating phenomena, and some and few perspectives. And I would like to mention other two things: a collaboration with Rob Stevenson and Giuseppe Carrer, University of Amsterdam, for uncertainty quantification, and with Dr. Federico Picchi now at the PFL in Lausanne concerning the bifurcating PDEs. And I would like also to mention the fact that all these studies and results are based on open source software libraries that can be downloaded freely on our website, matlab.cisa.it. And we are using multi-FENIS as an evolution of FENIS for also multi-physics problem, and all the algorithm and the error estimation, the greedy, and etc. Also the estimation of lower bounds that we are going to see today are in computing in this open source software library Erbenix, based on finite element FENIS solver. And this is another tool that can be freely downloaded, and it's available, ready to go with many also worked problem. Now, just to introduce simulation for the space-time, I collect here the notation that we are going to use. So we have a parameterization mu, and calligraphic P is the parameter space as a subset of RD. And of course, we want to find the state solution Y and the control U depending on the parameters. And of course, these are defined in calligraphic Y, big calligraphic Y and big calligraphic U as a space H1 0TY and L2 0TU. And I would like to mention the fact that we are going to introduce this cost functional to be minimized J, where we have, of course, to minimize this quadratic cost function, which is given by a difference between the state solution and a desired situation, which could come from data, collected data. And then, of course, we have a penalty terms here, which is allowing us to weight also the role of the control function U, if we want to minimize the influence of this control U, or if we want to relax a bit this opportunity. And of course, the constraint will be given by a state equation that is reported here with the general calligraphic big B operator. And of course, we focus on the fact that we are also in time. Once we have introduced this, I would like to say that omega is the general domain. Omega obs is the domain where we are introducing the observation, so the collection of data of the desired solution. And of course, we have also omega u, where the control is acting. At this level, we can use a Lagrangian approach, introducing an adjoint variable. And so we can define the calligraphic L as the Lagrangian, the sum of the cost functional plus the constraint of the state equation. And at this level, we can, of course, introducing the derivatives of L with respect to Y, U, and P, we can build our problem with the adjoint equation, the optimality condition, and the state equation. And this is our very general starting point. For the moment, Y is a general quantity as a state solution. We can think that it's a scalar one at the moment, and P is our adjoint variable. So this is the strong formulation for the general problem that we want to solve now. Of course, we have a space and time, omega, and then 0t. And you can see that the first equation is the adjoint one, the optimality condition is the second one, and the state equation is the equation number 3. We have initial condition, of course, for the state and the adjoint is backward in time, as you can see, with the final condition and not the initial one, and of course the boundary condition on the domain partial omega. At this level, existence and uniqueness of this solution could be proved thanks to the Bretzi theorem and the regularity for Y and for P. And if you want to go now into a discretization for this problem and also in a reduction for this problem, I would like to mention the fact that the first approach is based on saddle point formulation. And in the reduced order model, I would like to mention some work developed formerly with Federico Negri and others, for example, and also the work by Gerner and Verroy. And more recently, a work with Maria Strazzullo and Francesco Ballarino in Journal of Scientific Computing. The truth approximation that we can now use as discretization method is based on finite element and we will have, of course, a number of degree of freedom NH for a finite element and NT for the time discretization. So as you can see, the space-time discretized variable have an important dimension because there is the calligraphic n given. If we want to think how to solve this system into a one-shot unsteady system, we can see that we have the saddle point formulation. We can recognize the saddle point structure in this matrix. We have, of course, the state, so the state unknowns, the control, and the adjoint one. And what we can see that these are vectors where each element is given by finite element discretization, and for each we have, of course, the dimension of time. So this is very challenging and quite demanding in terms of the cost of this solution, because if we go to the real structure of this matrix that is reported in this explosion of these two metrics B and C, you can see that the one-shot, say, approach for this kind of problem is needing actually a computational reduction, because it's really unfeasible for real-time application and to have, let's say, good computational performance. So this is the main motivation for this kind of approaches. And if we want to just to have a look at the reduction, the structure is the same as the one that we have seen before. The main idea that it's reported here is that, of course, a full order discretization technique and then a reduced order discretization technique going from the calligraphic N to the capital N as number of degree of freedom. And with the delta, we indicate the state, the control, and the adjoint, so a very general solution. And the idea, the strategy is that we have, of course, the space-time formulation to build our basis, delta calligraphic N, and then with the reduced order modeling of dimension N, we are going to delta N. And this is the reduction in that we are achieving thanks to some methodology. And the idea is that, for example, the first one is based on proper orthogonal decomposition. Why we are doing this? We are assuming in any case that the discretization technique that we are using, so the error between the exact solution and the discretization one is going to 0. So we are having a very good quality classical discretization based on finite element. For the proper orthogonal decomposition, the main idea is that we have to select a certain number of parameters, compute this solution that are called snapshot, and then we will have to build, let's say, this to solve the generalized eigenvalue problem and to extract the eigenvalues and the eigenvectors. And the eigenvector will be our basis. An important effort also, and what I would like to say that it's very important that we are able, in any case, to keep a reduced dimension, much smaller with respect to the calligraphic one. And then we have also to pay attention because in order to fulfill some stability constraint for state, adjoint, and control, we have to introduce let's say, we are putting functional analysis into a Cartesian perspective. And the idea is that what we are going is to compute a new solution for a new value of the parameter based on projection of formerly computed one. So now we are ready to introduce several other aspects that are quite important for model reduction. I would like to mention that the basic would be found also into a very small book with Jan Staven and Benjamin Stam. And let's say a refreshed version also for time-dependent linear quadratic optimal control problem in a work also with Maria Strazzullo and Francesco Ballarino in Journal of Scientific Computing. If we focus now on the reduction side, and I wanted to introduce the aggregated spaces and the approach, we have always this saddle point structure, as you can see here, for the submatrix A, where of course we will have some studies to do, and then the two B and B transpose matrices that are building together with A the saddle point structure. The problem is well posed when we can of course guarantee the continuity of A and B and the coercivity of A over the kernel of B, and this is coming also from the space time formulation. In this case, we have also an in sub condition to be fulfilled, and this equivalent in sub condition also at the reduced level, because the structure is the same. We are just changing the global approximation spaces made up by our POD, the truncation, and then the number of eigenvectors that we have retained that are a number of capital N. We can see here that we can fulfill this in sup when the two spaces Qn and Un are equivalent. Usually are not, because usually for the state and for the adjoint we are using two different spaces. So this is something that we should somehow change in order to guarantee this in sub condition and to guarantee well-posedness and of course stability. So the idea is that we use some aggregated spaces for state and adjoint, and the idea is that Yn and Qn are the same because both are containing both the state basis and the adjoint basis. And then we have, of course, Un as an isolated space for optimal control. The dimension now of this problem is not capital N times capital N, but for a scalar version like this, we have 5n times 5n, because we will have, of course, for the adjoint and for the state solution, dimension equal to 2n, and then we have also the n dimension for the control. And this was already something that was introduced in former works with Negri and I would like then to provide you an example. And the first example that we are going to introduce, it's a time-dependent example with nonlinear equation, and it's an application to the coastal water 8 using shallow water equation. So for example, in this case, we want to recover some desired 8 and some velocity profile with a distributed control. The problem is reported here. So we have again a cost functional where we want to minimize two different quantities, the difference between h and the desired h, and the difference which is the a. And here we have the difference between some velocity field that it's assimilated with respect to the one that it's computed. We can see that we have a formulation in time and space. And of course, we have also, again, the penalty terms. The equation are reported here. You can see that are nonlinear equation. We will have as parameterization a convective field, the diffusion coefficient. Then we have the equation related with the elevation. And of course, we will have initial condition and the boundary condition. So I go now here just to explain better the role of HD, which is the desired situation depending on the parameter. The one that we want, the light blue is going to reach the blue one. And then, of course, here we have also, let's say, a function that could model the behavior of the bottom of this coastal zone. So this is the idea. We have three different parameterization: diffusion, convection, and also this elevation as an observation factor. And what you can see here in terms of data, we have an effective reduction, which is quite important because we have order of 10 as the reduced basis dimension compared with the order of, in this case, is 100,000 related with the classical discretization technique for this problem. Here you can see the solution of the shallow water problem. Of course, this is the finite element elevation and the reduced order modeling state elevation. And for different time step in this space-time formulation. And of course, the parameterization here is given for one family combination. What we can see also is that also for this kind of problem, we can guarantee a good convergence in terms of a small dimension of the reduced order modeling, and this is for the state velocity or for the state elevation and for the control itself. Here, we are at the limit of this methodology because we have a POD, which is quite expensive. It's a space-time formulation with POD, and we can see that if the error are guarantee very good accuracy, we can see that the speed up usually here is a little bit limited because we have flow control problem in a time-dependent nonlinear setting, and we have also the further burden which is given by the aggregated spaces to guarantee stability. But in any case, the full reduction that we have is in any case guaranteeing a very good, let's say, computational performance. We are going to improve this with this following proposal that it will be based on, let's say, space-time greedy algorithm. For the results about shallow water and details about the numerical analysis, I would like to mention you the fact that there is this recent work in the Journal of Numeric Mathematics with Maria Strazzullo and Francesco Ballarin. And then there is also this topic is treated always with Francesco and Maria Strazzullo into a new chapter of a new volume of the handbook on dedicated to optimal flow control. A smarter algorithm now will be based on space-time greedy for parabolic problem. And the POD drawback, as I already mentioned, is that it's quite costly in order to build these matrices to solve the eigenvalue problem and to build the spaces in the aggregated spaces. So we need to improve this and also to have a few analysis ingredients that are ready to go and are helping us in improving the, let's say, the computational performance and also the analysis of the problem itself. So the idea is to use a no-control framework. So for no-control framework, I mean that the first problem is the one that we have solved before, where we have a joint optimality condition and state equation. And we are going to introduce and to replace the control in the state equation, and we are going to have this no-control framework, eliminating the optimality condition from the system. And of course, this will be recovered then in a post-processing. So that's why we are going from a POD let's say, approach to a reduced basis, a more classical reduced basis approach that now we are going to introduce. The weak formulation for this kind of problem for simplicity is recollected in this compact, let's say, notation where we have the optimal control operator for the full problem, which is indicated with the calligraphic big B. And we can, of course, also in this case, carry out studies about existence and uniqueness of the solution. And this is done thanks to Nakash-Babushka analysis. And again, there are, of course, some regularity on the state and on the adjoint. And I would like to mention in literature some approaches by Langer, Steinbach, Troeltsch, and Young, and also more recent work by Karsten Urban and Anthony Patera on the space-time formulation with the error bounds that we are going to use. So the space-time system is reported here now. So you see that we have simplified, we have compacted a little bit. We have only Y and P as unknowns now. So the control will be recovered as post-processing. The algorithm that we are going to, of course, on a greedy philosophy, but now in space and time. And of course, we have also to take into account that we need, again, aggregated spaces for state and adjoint in order to be able to guarantee the stability for the fulfillment of the in-soup condition. And I think that I've already mentioned the literature here, so we don't need further information for the moment, but I would like just to give you a general overview of what will be done in the global space-time setting. So again, we have to compute and to solve our problem for some value of the parameter in order to get our truth solution delta n, which is the state and the adjoint. The strategy will be to be able to control the error between finite element and reduced order modeling. And this will be given thanks to an error bound delta n. Delta n is given, and I will introduce later. So for the moment, the idea of the classical greedy algorithm is that we will start from one configuration of the system, U1. We will solve the full order model. We will use this as solution, and we start to build the two different space for the adjoint and for the state solution. So YYN and YPN. Then into iterative algorithm, we are going to select the nth value of mu. So the one that the candidate snapshot that is going to be part of the reduced basis for state and adjoint will be given where we have the maximizer for the error bound. So in the worst case scenario, where things are not going so well, we select the new value of the parameter. And we are building aggregated spaces. So once we have the space for the state and for the adjoint, we will put together in order to have our space, aggregated space YN. And the algorithm is continuing thanks to a tolerance, but the idea now is that the capital N, it will be because we are building this into a more efficient way with respect to the POD. And the idea also is how to build these error bounds. And error bounds will be given thanks first of all to the creation of and the computation of the residual of the full optimality system, which is reported here. So the difference between the two operators, the state adjoint operator and what we have in the right hand side. And in this case, since we are not focusing on a saddle point formulation, we are operating on a more general in-soup, which is the Babushka one on the full operator. And in this case, this one is also collecting state and adjoint. So the idea is that we have to be able to manage also with this in-soup into an efficient way in order to be able to introduce our error estimation, which will be based on the dual norm of the residual divided by this in-soup. And this is by definition our, let's say, error bounds. Of course, beta is very expensive to be computed, also in the steady case. If now we go from the steady to the unsteady case, so we had also integration in time, as you can see here. The residual is a little bit more involved, and of course also the definition of this in-soup is much more complex in order to account also the presence of an unsteady problem. And concerning the, let's say, the error bounds, we are going to replace beta with parametric lower bound beta LB, and this will be our focus in order to be able to carry out a good error analysis a posteriori error analysis for this kind of problem. And so we need something which is cheap to be computed. And the work and subsequent now is based on a more recent work, always with which is submitted, but it's available also as archive report, and is based on certified reduced basis for linear parameterized parabolic optimal control problem in the space-time formulation. And here we report also that one of the possible recipe that we have proposed is based also on the fact that we have developed a lower bound for beta, which is quite effective and efficient because it's not depending on time. And it's given outside the, let's say, when the controllability and observability are equivalent, we can use alpha as a penalization, and then the coercivity constant on the operator A. Otherwise, we can use these other quantities, which are based on the continuity constant on the operator C, on the control operator U, and again on the coercivity. So the idea is that we have some quantities that are a little bit easier to be computed. I don't go too much in details, but you can take into account that we have used this as error bound, and I will show you also the effect of the lower bound over the real beta value. So this let's say formulation has been tested in this Graz flow, where we want to achieve a desired temperature field with the boundary control, and we have also a parametric geometrical framework. So before going in the presentation of this equation, I go on the geometry. So the idea is that we will have an heat flux entering with a convective field. We have Dirichlet condition here, so the temperature is given, and at this point we will have some control flux entering in order to exchange energy, to exchange heat rate, and we will have two zones where we can observe the behavior of the temperature, and we can reach a desired value, and this is the outflow. So the parameter is acting on this geometry, the length of the red dotted wall, for example, where we are acting with the control, and the other two parameterization are given in the convection advection ratio. So it's mostly related with the Peclet number, mu1, and mu2 is as already said, the geometry, and mu3 is the observation. So the temperature that we want to reach in omega 3 and in omega 4, which are our observation zone. And I go back to the equation. The minimization of this cost function is quite standard because we want to minimize the desired temperature with respect to the computed one. Again, we have a time-dependent problem, and we have, of course, the fact that we can also balance the role of the control. And this is a time-dependent advection diffusion problem with the parametrization and the parabolic distribution of the convective field. And for insulation, we use homogeneous Neumann condition. Otherwise, where we have heat flux, we have the control in a Neumann control in the zone where we want to change our exchange of rate. And of course, also we have some zone on the Dirichlet boundary condition for the temperature. Here you can see the comparison between high fidelity and reduced basis state solution and the adjoint one at a different time field. So you see that we have this thermal boundary layer at the second one, and then you see from second 3 the diffusion that is happening, and of course also for 0.5 seconds you see that the diffusion is even completed, and the two boundary layers now are merging. For this kind of problem, we can see that we need a relatively small number of basis function, and we can see that the error between the given by the true beta and the lower bound is in good agreement, and in any case it's the same order of magnitude. And I'm going to focus this in the subsequent slide. I would like just to mention that the effectivity for this kind of problem is ranging from 10 square to 10 cube. The speed up is quite important, and of course again we can keep at a reasonable level of complexity the reduced basis number of, and this is quite important because in any case again we have a flow control problem, so we have a state adjoint formulation and we have a space-time formulation. If we want to go to check also the computation of our beta lower bound for different test cases, so one without geometry, and also this case here it's even a distributed control. in the steady case, we can see that it's clear. The same color is representing the beta and the lower bound of beta. We can see that there is a very good separation of them, and the behavior and the trend is quite clear, both in the steady but also in the steady case. And in the tables for the error, we can see that the relative error in any case is and the separation and the use of a lower bound is not influencing so badly our problem, but it's simplifying our computational cost, giving us the possibility to have a reliable error bounds, and at the same time the performance is really acceptable in terms of order of magnitude for the error. And this is true in the steady case, and also in the more complex case where we have geometrical parametrization and where we have boundary control, which is usually a little bit more complex to do. And again, we can see that there is a very good separation, a very good behavior with the lower bound with respect to the upper bound, and for several value, you see here that we have some range of variation of the parametrization mu. And this is for different mu2, so for different geometrical parametrization, mu1 is the Peclet number. And I would say that the same is also for the effectivities of this problem, that usually the order of magnitude of the relative error using the lower bound and using the real beta, the Babuskin soup, is in good agreement for the steady and the unsteady case. Now I would like to mention some application for sciences, and the idea, as I've already mentioned, is to carry out also some uncertainty quantification, let's say computation and characterization of the problem in this parametric setting. And the idea is that the parameter now is a random input, so a random variable, and there is also a given probability. So there is a probability density distribution, which is indicated with the rho. So we have an uncertain input, and we have an uncertain output based on usually on the control and on the state solution. Usually we need to compute some evaluation of statistics on the optimal solution, so the expected solution. And usually the classical approach is based on Monte Carlo, which is Monte Carlo is characterized by lots of realizations. And the idea is to use here a weighted reduced order modeling approach in order to accelerate this Monte Carlo methodology. And we have, of course, two possibilities. One is to weight the solution during the construction of ROMs, because there is a probability density function, so not all the solutions are characterized by the same weight. And then we can also sample the parameter space during the construction. And the idea is that usually for this parameterization, for this distribution, we have this Gaussian distribution based on beta function, and this could be wider, of course, smoother, but some of them could be quite picky. So usually this is what we can do, and usually when the configuration is a little bit more picky, we have alpha and beta bigger, like we can see here. And this is a very different distribution with respect to not this one, but the constant one, for example, bringing a probability equal to 1. So the idea is that we take our POD algorithm, our classical approach, which is reported here. The POD is minimizing an L2 projection error, and the idea, of course, and this is the discretization of this algorithm in this parametric space, but the idea is that we want to change something here to have a better suited approach and algorithm for this kind of problem. And what we can do is, first of all, to use a more general quadrature rule to have a good approximation of this integral, thanks to the fact that we will use as the sample in the parameterization the nodes of the quadrature, and then we will have, and these are our mu, of course, and then we will have omega, which are going to be the weights of this parameter, of this integration. So the idea is that if you want to extract the expected value, and of course, based on this error, what we can do in the discretization of this now on this integral with this rule is that we will have this kind of development, since we will have the respective weights, and we will have the nodes of the quadrature, and of course we have also the probability density function. So the idea is that we are using this weighted approach, and this quantity is indicated with W. So also our correlation metrics and our POD approach will be based on the fact that we are correcting somehow our inner product to build the correlation, each space in the correlation matrix with the square of this W, such that we are keeping into account that also we have not only the weights coming from the quadrature rule, but also the weights of the probability density function. So if you want to use this approach into an optimization problem, we had some cooperation with the National Institute for Oceanographic Studies in Trieste, and we decided to have some studies of advection diffusion in the Gulf of Trieste. We wanted to simulate, for example, some release of pollutant in the port of Trieste and study the impact of this release, for example, in this red zone, which is close to the castle of Miramare. The idea is that we have some parameterization, and the parameterization could be characterized by, for example, the wind action. Trieste and the Gulf of Trieste are very well known for the gusty wind in winter and summer. And so the idea is that we were taking into consideration the parameterization of this wind action in the diffusivity parameter and also in the advection field. So we have this kind of parameterization. The cost functional is very standard, like the one that we have already seen for the Graz flow, and the equation also is a scalar equation in this case. And the idea is that we have these different parameterization for convection and advection terms. And here we can see that we have different solutions without control or with control. And the idea is that for this kind of parameterization, where we have this random input, the selected, let's say, approaches on not only on Monte Carlo as an example, but the other, let's say, quadrature rule are in good agreement. And if we have a look at we do the analysis of the convergence for this kind of methodology, we can see that the weighted approach in orange is giving us a better convergence. So it allows to reduce also the number of basis functions. And the idea is that we are comparing this with a non-weighted approach in blue and a weighted approach, but based on a beta function, which is not very peaky, beta 0.505. So the idea is that the introduction of this correction, a weighted approach for some problem with random input is better, and we are going to have better performances on this kind of problem. If you are interested, these details and many more examples are contained into a recent work with Bob Stevenson on a paper on computer and mathematics with application last year. Now, I would like, in the remaining part of time that we have, I would like to present you another perspective. It's a new one for us, where we try to combine in a reduced order modeling approach flow control and bifurcation in nonlinear PDEs. They work also in cooperation with Federico Picchi now at the PFL. And this is well known also in many phenomena in nature that are called the Quandt effect. So the tendency of, let's say, a flow to be attached to the wall, and the hug effect. And this kind of phenomena has many applications in aeronautics, also can be observed in nature, but there are also, for example, in the human being. For example, if you study the mitral flow, and so we have a regurgitant flow from the ventricle to the atrium, so an opposite blood flow, because we have a leaking valve, for example. This phenomenon is quite well known, and also in the echocardiography is creating some problem, because if we are losing the symmetry of the flow, sometimes the echocardiography is not working well. So this is something that has also an application and also motivation in medicine. The idea is that we would like to control the bifurcation. So when the flow is changing its, let's say, configuration, and when we have loss of uniqueness of the solution, and for the same value of the parameter, we may have two or more solutions. So the blood flow is modeled with the classical Navier-Stokes equation. In this case, is even in the steady case, and also the mu as the diffusivity. And this is the classical setting with the nonlinear terms initial, with the boundary condition, and on the inflow, which is a Poiseuille flow actually, and then the Dirichlet on the other part of the wall, and a zero stress condition, which is reported here on the outflow. The idea is now we have also a small movie that while I'm talking, you will see that one of the flow is losing the symmetry and it's going to be attached to a wall. You see the upper wall. So for the same value of the parameter, we have this bifurcation. It's a pitchfork bifurcation because we have this wall this flow attached to the upper wall, and then we may have also the one attached to the lower one. And also we have also the unstable branch, which is reported here, which is the continuation of this symmetric configuration. So we have this kind of approach, and we would like to better understand if with the flow control we can limit the bifurcation, so we can keep the solution where we want, for example, a symmetric axial symmetric flow, or if we want, for example, to endorse this bifurcation and endorse some configuration which are non-symmetric. So the idea are reported here. The first one is a pitchfork diagram, and you see that when the diffusivity is diminishing, so the Reynolds number is augmenting, at one point you have this pitchfork bifurcation, and you see that you have the flow attached to the upper or to the lower wall, and then we have this unstable branch also continuing to exist if we are using a perfectly symmetric discretization, or we can use high order, for example, discretization technique. Our ideas are based on the fact that we were studying also the linearized system and the behavior of the parametric behavior of the eigenvalue. And what we can say that if let's say eigenvalues are moving in the imaginary axis and are not crossing the imaginary axis here, but they are staying in the part of the imaginary space where we have a real part close smaller than 0, we have stability. Otherwise, if the one eigenvalue is crossing the imaginary axis here, you can see that we have this kind of behavior with the pitchfork. This is also true in the unsteady case. In the unsteady case, we have off bifurcation because we have conjugate eigenvalues, imaginary eigenvalues that are crossing the imaginary axis. So this is something that has been already studied for other kind of application and approaches. What we wanted to do here is to use an optimal flow control. In the past, we were able to introduce this kind of problem with parameters, and we were able to study the effect of the geometry to delay or to enhance and anticipate the bifurcation. And on another side, I would like also to mention that we had also some studies in multiphysics where we were able to delay the bifurcation thanks to, for example, in a multiphysics setting, using different combination of parameters. Here we are using flow control. So our idea is that with control, we can endorse or limit the bifurcation and keep the desired configuration. The control problem is a classical one. So you can see it's an Navier-Stokes problem. We have a control operator. The control could be Dirichlet or Neumann type, and then I will show you example. And of course, here we want, for example, to impose a desired velocity field, a velocity profile, which is based here on an observation section that we are using. For example, we can use a symmetric Stokes profile, since we are using is in the inflow a Poiseuille flow, or we can use some axial, let's say, axisymmetric velocity profile. So this is something that is contained in our, let's say, data VD. The first idea is a control in the Neumann type in the outflow, of course, and then here we can say we can decide to keep this or to enhance this configuration. We have, of course, two different possible solutions, and this is working quite well, even if, of course, I have to say that the penalty is responsible this year. We are putting a small penalty, so we are controlling a lot of this system because we are not minimizing the effect of the control. And here you can see what is going to happen to the velocity profile, the controlled and the uncontrolled one, and the symmetric and the asymmetric one. And of course, the role of the control in the outflow. The same could be done with the Dirichlet for different value of alpha. Of course, here we can have more influence on the control because we are also using flux entering in this zone. With the Dirichlet, we are imposing a velocity and not only in the inflow. And of course, also in this case, we can even keep everything in only one, keeping only one branch and to avoid the bifurcation. Here it's maybe a little bit more clear that if we have a spectral analysis of the parametric behavior of the eigenvalue for the uncontrolled Navier-Stokes, we have a stability here, or the fact that we are crossing the axis, we have an unstable branch. But it's more clear that let's say if you are using the Dirichlet controlled Navier-Stokes, we have this case where we are crossing the axis, and this case that we are keeping things in the symmetric part. So we have plenty of option and solution, and can, of course, being able to understand where going with our system, what we can do with a control approach. I would like just to give you, in the last minute that I have, also some idea about advances in the development of flow control problem in both in, let's say, in model reduction with random inputs. And recent work with Davide Zoccolan and Maria Strazzullo is based on the fact that we are also introducing some, let's say, smart stabilization for transport dominated problem, when we need to do an offline-online stabilization. Then, in order also to have other approaches in, I'm not giving more information here because I don't have time, but in the data-driven and so in non-intrusive approaches of reduced order modeling, I would like to mention the fact that with Nicola Demo and Maria Strazzullo, we are also applying an extended framework to optimal flow control with the physics-informed neural network, the so-called PIN. And also we are using as another potential reduction technique based, which is named dynamic mode decomposition, DMD, in time-dependent problem with Eleonora Donadini, Maria Strazzullo, and Marco Tezzele. We had some application and approach to this data-driven partitioned approach in optimal control. And so the idea is that at the state of the art, as you have seen here today, we have developed reduced order modeling with the numerical analysis, a posterior error estimation, lower bound for the IMSUP approaches for a non-linear and time-dependent problem. The non-linearity also has been checked on Navier-Stokes equation and shallow water equation, and the linear case, you have seen the Gratz flow and standard advection diffusion problem. We have proposed a space-time greedy with a posteriori error bound. And in the perspective, we have, of course, more application in environmental sciences, considering also a joint project with Giulia. And we need to better understand also the fact that we can use automatic learning algorithm to have a better enhancing between input and output relationship and system. And we do think that for many problems, also a non-intrusive approach would be better in terms of computational performance and also feasibility. I would like to thank you for your attention. Of course, now I am available for questions. Thank you.
Très bien, merci Gianluigi. C'est un exposé impressionnant de quantité de travail. Très belle présentation. Et donc, je pense qu'il va y avoir un certain nombre de questions. Donc, on peut poser les questions, lever la main si vous voulez. Page 16, tu as parlé d'effectivité, mais tu n'as pas bien défini ce que c'était. Moi, je ne l'ai pas compris. Est-ce que tu pourrais revenir dessus, s'il te plaît?
The effectivity is the ratio between the estimated error and the real one, the one that we should, of course, it's a quantity which is done as, let's say, exercise. It should be greater than 1, because if we go below 1, it means that our error bound is unfeasible and it's unreliable. And usually it's, well, of course, having one dot something is good, having 10 is acceptable, but usually for this kind of problem, when we have also geometrical parametrization, it's good to keep under control this between 2 and 3 order of magnitude. And I know that this could be strange, but for complex problem or where we have a complex parametrization, it's quite normal to have this kind of effectivity. And
so here you have 10 to the 2, 10 to the 3.
Yes.
Yeah, okay. So which is
in engineering is very important, because we are guaranteeing the fact that we have a good approximation of our problem and we have a safe margin. So it's accepted in the real world in application that we have this. Of course, in order to be able to have smaller effectivity, we should keep the problem quite simple in terms of parametrization. Usually, geometrical parametrization is responsible of the increase of this effectivity, or we should keep the range of variation of the parameter under control, and it means that we cannot change the order of variation of parametrization of more than 1 order of magnitude. If we start to have this important range of variation for the parameters, to have very good effectivity, we need to introduce some reduction in parameter space. So it means that we have to simplify the parameterization, for example, with some active subspaces, other approaches. In that case, I think that we are really able to clean also a complex problem and to keep the effectivity at a very reasonable level. But we need more efforts in terms of reduction in parameter space. So a good agreement is to have a compromise between these two different needs.
Okay, and so the fact that this is effectivity is pretty large, so I understand it from the point of view of the complexity of the problem, which is a real one, but shouldn't it be improved if you have a better evaluation of the beta constant,
Yes.
the beta LB, okay?
Yes, so, assume that we are able to have a good capability in computing residuals. We assume this, of course, the responsible of the, let's say, of the explosion of the effectivity is the behavior of the lower bound of the INSUP. And here it's a compromise of computational cost of having a good lower bound, on having, let's say, I can show you also where is going to happen this, or having a compromise that it's in any case acceptable. Here you see in the time-dependent case, you see where you have the real beta and the corresponding lower bound, because they are paired by color. So
there is at most one order of magnitude of difference.
Is 2. Here it's at least 2 order of magnitude.
Two order, okay.
Yes,
okay,
here it's 2.
Okay, so it's really the main reason to have a better evaluation of the answer condition. Okay.
Yeah, this is, and the fact that also we have something that is not independent. And if you have a look here, we have also another role played by alpha, because also alpha, the penalty that we are using in the cost functional of the optimal flow control problem, is playing a role, because if we put alpha big, you are let's say minimizing also the role of the control. If alpha is very small, you are leaving the control much more freedom, let's say, to be able another balance. It's also related with controllability in any case. Let's say maybe it's a 2 order of magnitude the beta lower bound, but also 1 order of magnitude the controllability.
Okay, thank you. Albert, une question? Tu remets ton micro?
Oui, hello, Gianluigi, thank you for your...
Bonjour, Albert.
Bonjour. So my question, generally speaking, the success of reduced order modeling of this type is, we know it's tied to properties like K of width, the parameterized family of solution, or in the case of POD, of the eigen value, the covariance operator. And so in the examples that you have tackled here, which are complex, do you have a theoretical understanding of these properties, especially with geometrical parameters? You know, how far can you analyze all this?
It's a very, very interesting question, because I think that, well, you are the expert first, but I would like to say that the geometry is influencing, and all these results could be improved if we would introduce in the transport-dominated cases the possibility to have not only a parametrization map, so a transformation map to a reference domain if you have the geometry, which is basically what you mentioned, the first element of complexity and spoiling of the, let's say, of the convergence and the n width is basically the geometry. But also in the transport dominated, we are studying the possibility to have a transport map to report our different configuration for different value of the parameter to a reference physical configuration. So in that case, we should improve a lot, and we should reach a better performance, which is closer to the one that we could think when we have the simple parametrization. Of course, I am afraid that to do that, we need to go more deeply inside some automatic learning technique to be able to do that. But I think that there are already some ideas around in some groups of research carrying out this. Otherwise, yes, I think that geometry and also the transport domination is spoiling the success of model order reduction.
Okay, Thank you.
Thank you.
Olivier?
Yes. Can you hear me, Gianluigi?
Yes, yes. Bonjour, Olivier. Bon après-midi.
Oui, alors très bonne conférence, formidable. Hein. Le travail que tu fais, c'est impressionnant. Okay, I'll speak English anyway. I have a question about the memories. When you construct your space-time basis, do you have to store all the trajectories of forward and backward in time for the state and the adjoint?
This is a limitation. This has been a strong limitation in the application of flow control problem in the time-dependent context, because at the beginning, when we were in the steady linear case and we had to go to the non-linearities, of course, there was a concern. We need a generation of PhD students, not to go further. But of course, what you mentioned is still a problem, because also in the classical discretization technique, the adjoint problem is going backward. So you need to start from capital T and go back to zero. It's a backward problem. So yeah, this is something that it's still there.
Yes, by the way, may I suggest that you look at the work of Gribank, because for automatic differentiation, they have the same problem. And they have some meeting points of this complicated thing, but they have been able to reduce the memory size.
Oh, okay. Yeah, we are basing this on some preliminary work by Schoberl, and because they were group. Unluckily, some of that work were not well spread. Also, and also to find them, some of them as a technical report. But yeah, we will check this. I have to say also that everything has been implemented without using some automatic differentiation algorithm already available, but everything was inside the software that has been created, basically mostly in the PhD thesis by Maria Strazzullo.
Okay. Other questions? So in the same direction, isn't it possible to have snapshots in time and then have the coefficient that depends on time instead of storing all the trajectories, both for the forward and backward problem?
Yeah, this is the idea of also applying some now automatic learning to this, and in order to have more intelligent management of the maps between let's say the real time, the online system, and the solution, to have an input, to have a real black box. If you remember, Yvonne, we were calling black box before we had at the end also something inside which was based on some automatic learning. Now I think that the name is really important, and I think that yes, we can do that. We can do that.
Okay, this would reduce somehow the size of the storage.
Yeah, I have to say also that what I wanted to give you today was a more numerical analysis orientation, in order to have this error analysis, the lower bound, also the several approaches of the beta and soup from Brezzi and Babuska. So I wanted to stay more on classical numerical analysis, but of course we have also some recent development going, also automatic calculation of the coefficient as a response surface and so on. But I wanted to stay more on numerical analysis, looking at the place where I was delivering the seminar.
Okay, thank you. And so maybe a last question on my side would be, so you are speaking on page 26 about strange flux. So what is this, page 26?
No, it's strange flux because this is the limit of a problem, which has been changed a lot, because we are enforcing the fact that we are imposing also flux entering into a wall that usually is related treated as a wall. So it was let's say a limit test case to check how we can impose controllability on this system and what we can get. So this was the reason.
The strange flux is you have an inflow at the orange part.
Yes, exactly.
Oh, yes.
So we were enforcing also here.
Okay, where you force the symmetry in some sense.
Yeah, it's like we were making a soufflage.
Mm-hmm.
yeah, this was the limit. We were because we are somehow changing the nature of the problem, but it was just to understand the role played by the penalty, to play the role by control over the bifurcation. We were quite interested in this problem because we have studied also in the multi-physics context, and now we are trying to do this also in the compressibility context. And there are several interesting things to go more deeply inside, and one was related with the combination of using control to keep the uniqueness of the solution in certain parametric range, for example.
Okay.
Well, because we think that also there are nice potential application for this kind of.
Okay, no more question. Okay, so I think we can close this seminar.